Hi everybody. Let's go look at more of complexity of algorithms. And I asked you to look at two algorithms that we have seen in the past. So I hope you found the references for it. So the first one is number 25, is a ternary search. Now I want to show you that you can analyze the complexity either from the description of the algorithm or from the pseudocode. So I'm going to do this one from the description. So the ternary search, what does it do? Well, you remember the whole thing is given a list L of objects and an element X, a sorted list. I should add this. This is of course very important. A sorted list, and X is there in an object that could or could not belong to the list. And what we want is the out. So that's the input. And so our output, as I said, I'm describing the algorithm, not giving a pseudocode. The output is the location, the variable location, which has two possibilities. If it's 0 means X is not in L, and if it's I, that means X is the ith, and the list is given as A1, A2, up to AN. Therefore can say it a bit quicker, right? So X is AI. And so these are ordered, so perhaps even to emphasize that, okay, let me list them as an ordered set. So as a sorted list, A1 less than A2 less than A3, all the way up to AN. And of course, the complexity here is always in terms of the size of the input, N. Okay, so what does that do? How does the binary list work? Well, we have our list, so we have A1, A2, A3, and I don't know far, I'm going to put here A27. Why do I take 27 and not, you said before you take this 16 and stuff like that, why 27? You will see why I like to do that. Okay, so what happens? What do we do? We know that these are ordered, and so the ternary, that refers to 3, right, 1/3, says divide this list in 3 equal parts. So you divide in 3 equal parts, so let's see what would be the first 9, then you would have A10, A11, and so on, and then this would be this would be A9, right, this would be A18, this would be A19, if you think about it, and so on. So we have, I'm just listing the ones before and after the division code. And then you do 2 comparisons. So 2 comparisons. So the first thing is divide in 3 equal parts, or almost equal, right? You cannot really do this if it's not a power of 3, or a multiple of 3, but divide in 3, put equal between parentheses, between quotes. Some might have 1 or 2 less, but that's not so important. Or you can always add a couple of extra stuffs to make sure that it has the right amount. That's the first thing. Then 2 comparisons. Namely, you're comparing it with this element and with this element. Now, okay, at the moment there are A9 and A19, but I should be careful. What it will happen is eventually I will have a list that remains. This is the remaining list. And that is the list that I divide in 3, and then I take the element that is located here and the element that's located here. Those are just some choices you make, but that's how the algorithm works. And you compare X with this element. You ask, is X less or equal to this element, or is X less or equal to that element? And of course, depending on the answers, you know exactly there are 3 possibilities. So we have 3 possibilities. Either X is in there, X is in there, or X is in there. Perhaps let me do this in different color that you see what I mean here. So these are the comparisons, right? So the 2 comparisons that I was talking about, these are the 2 comparisons I'm talking. And then let's do it in different color that you see that what I'm doing here. So there are now 3 possibilities. It could be X is somewhere in this list, X is in this list, or X is in this list, by the comparison with these 2 elements. And then you continue. Okay, so how are we going to analyze this? Well, you notice, as I said, why I like this to take 27 here. Let's think a little bit about a possible scenario is Suppose you somehow found that x was in the first part of, let's say in the second part of the list. Suppose you say, okay, after one step, this and this goes, and I'm looking in this remaining part, which I divide again by 3. Now, these are how many elements are there? If you think about it, because 27 divided by 3 is 9, right? So I can, again, equally divide in 3 parts. And that is why I prefer to take a power of 3, because I can keep dividing in 3 equal parts. As I said, it's not necessary, it just makes the argument a little bit easier. Mathematicians do this all the time. They say, okay, let's make the argument easier. And you can, I told you, you can emulate this, you can simulate this by adding some dummy elements, either all the way in the beginning, a couple of zeros. You say, okay, we know that's never going to be those elements, but just to have the right amount. Okay, so let n is a power of 3. I'm going to think of n as a power of 3. And then I'm going to think, how many times do I do this? Well, each time I'm going to divide this thing in 3 equal parts. Okay? That's divide in 3 equal parts. So after I do that, what's this? What's the size? 1/3 of the previous one. Okay? So this will have now size 3k minus 1 after one step, right? That's what we said. This is 9 elements now. If I do this again, say now this is the result. This is what I was trying to say here. Divide again, what will be the size of one of these things? And now suppose we end up in here. So turns out in our second choice, we end up in this part. That means now what's the size of this thing? 3k minus 2, and so on. So how many times do I have to start dividing? Oh yeah, I should have said, what happens if I can no longer divide? Namely, when do I consider no longer divisible? If I have just one element left. And if there is only one element left, I know exactly what to do. Look at that element. If it's my x, yay, I put that as my location. If it's not my x, I know x was not there. Okay, so how many times do I have to do this? So the number of divisions, but divisions in 3, partitions in 3, divisions in 3 parts, until I have one left, exactly k, right? Think of 27. That is, 27 is 3 to the 3rd. You divide it once, it becomes 9. You divide it twice, it becomes 3. You divide it one more time, it becomes 1. And then you stop. Okay. So the number of divisions is k. And then what do I do? So in other words, that's part of the loop, right? And then what do you do? Well, then it says here, you do 2 comparisons, and then you erase in our scenario we said, okay, it was in the 3rd one, so we erase these 2, which just amounts to, if you remember how the algorithm works, adjusting these 2 endpoints. These 2 points kept track of where in the list you are, and so because of this you say, okay, this guy now becomes this guy, and this stays where it is. And in the first time we had to move the original endpoint and the back endpoint here. If it's the middle list, then this one moves there and that one moves there. So another 2 steps, or 3 or 4, depends on how much you see this. So the inside, when I have to do things, well, I have to do 2 comparisons. After I do the division, right? I do 2 comparisons. Then I do 2 or 4, whatever you call, more assignments to make the endpoints the right way. And that's it. That's 4 or let's say 4 steps. And I have to do each time, and k times I'm going to do this. So all in all, so all this is 4 basic steps. Okay. So I see that the complexity is 4k. Now that's the bulk of the thing. Now remember, once I can no longer divide, I have to do a few more things. I have to check whether this element that I'm left with is x. If it's so, then I call that the location. If it's not, I give the location equal to 0. So perhaps 2 or 3 more steps. I'm going to set for the heck of it 3. Why am I so cavalier? Why am I so careless about these, how many steps? Because we know that constant do not contribute in complexity. So the complexity of this is the same thing. So this is O of k. Okay, but I want to say it in terms of n, remember? So what is k here? How do I find what k is in report to n? We have to now get to k. Remember, we do the inverse function of exponential is to take the log. So we have the log 3 with base 3 here of n, that is k. So, conclusion, we have O of log 3 of n. What does that mean, really? Well, remember, the log 3 of n is the same thing as the log 2 of n divided by the log 2 of 3. I think I have it right. I might have it wrong. I always get this formula a little bit messed up. I think I have it right. Meaning, this is a constant here. So up to a constant, these two functions are really the same. So this is also the O of log 2, but we don't write it 2. In computer science or in discrete math, our logs are always with base 2. And I have mentioned this before, that the log with any base is the same as the log with base 2, which is the standard convention to take. So this is of base complexity log of n, which is, as I said several times, is much, much better than time n. We have now talked about complexities, polynomial complexity. This would be n, right? Many of our searches were complexity n. You basically just went through the whole list and until you found it. Worst case scenario, you had to go to the whole list, so n steps. But that is too many steps. You can do with log n steps, which is way, way better. Okay. So that was that one. And then the other one was about the scheduling project or procedure. And here I want to do how the pseudocode was. Remember, I took a different pseudocode than the textbook, although the complexities will be the same. So if you want to look at the textbook and verify that and see whether you get to the same conclusion, what the complexity is. But let's look at the pseudocode that I gave. So I remind you, what we have is a list of talks. And these talks are basically given by two numbers, two time stamps, namely the beginning of the talk and the end of the talk. And we have to schedule them without conflict. And we use this greedy algorithm. So greedy, which kind of, I'll tell you when I describe a little bit why we say it greedy, with respect to earliest end time. Now, I went to great length in explaining that it's actually rather counterintuitive, that this is actually the optimal strategy. This is the best strategy. But if you use this algorithm, you will get the best solution in the sense that you get the most possible scheduled talks. I gave you an example. It took me a while to get it straight, but there is an example, and I hope you checked it, that it was correct. So the earliest end time. So what the idea is this. The idea is very simple. Once you know that you have to be greedy. What does greedy mean? Well, you take the one that has the earliest end time. That is the greediness. I want to have the one with the earliest end time. I want to get rid of it as soon as possible. Think of it that way. Okay? Let it be over as soon as possible. So the one with not the one that you might think, oh, I should take the one with the earliest start time to get over it as quickly as possibly over it. But if the one with the earliest end time could go on for 3 hours, right? You want the one that ends the first. You say, why don't you take the shortest? Yeah, but that might start at 11 o'clock, and there you're sitting from 8 o'clock there, twisting your thumbs and waiting for that talk to come. No, you want to take the one that ends the earliest if you want to go home, right? That's the greediness part. Okay, so what you do, you go through a list. So here is the procedure. As I describe it, I'll also give the pseudocode because it's very much similar. So we call this hall schedule, or don't forget now, or lecture schedule or something. And so this contains this list of talks. Okay, and so the first step was what we will do is keep throwing talks out that are no longer possible to schedule or have been scheduled. Okay, so we will change our list, and therefore we have this. We are allowed to do this while here, while the list is not empty. And we know at some point the algorithm is going to make this list empty, and therefore it will jump out of this loop. Sorry, this should have been aligned. This is to be aligned. Sorry. Hello. Okay. No. All right. So there we go. And then what you do, the first thing is. And here we use a little bit of description, but we can do this in pseudocode. Find talk t with earliest end time. That is exactly what our greediness tells us to do. We talk t with earliest end time. I'm describing the algorithm. Then we will talk about complexity, okay? That's the first thing. The next thing, I put here dots just so you see that there are different things, but of course in a pseudocode you don't have to do that. What we do then is we say, okay, that's the talk I'm going to do. So I'm going to add that to the schedule. Oh, that's what I forgot. I have to initialize the schedule. I'll make the schedule empty, and in the schedule I'm going to put talks. So of course there's going to be always at least one talk in there, right? So, well, that's assuming that there are talks and that none of the talks go beyond the time that we are allowed to schedule, but okay. So, so I add this to my schedule because I have probably in the meantime already found some text, and this is the crucial thing now. What else do I have to do? Remove all talks that are incompatible with T. And I'll remind you again what this means. Remove all talks, I should say, from L. That's what I meant, of course. Not from S, of course. S, I'm not going to touch that. I'm going to only add to it, never remove. Remove all talks from L that are incompatible with T. And what I mean is, well, if they overlap, if their time schedule overlaps with that of T. And when I say remove all talks, I also, of course, mean T, to remove T itself. And that's it. There's actually nothing else done, because when the list is not empty, I will find something, I'm going to add it to my schedule, and when the list is empty, I've done. I found the best solution. So I'll put here a return. I think I looked at the video again, as I think I forgot to put this here. Return S. I said it, but I didn't write it down. Okay. So now comes complexity. First of all, of course, what is the complexity in terms of the number of talks? We always talk in the size of the input. I have argued that there are different considerations, but just to let's agree that we always talk about the size of the input. That's normally what causes the most problem, is the size of the input. Okay, so let's see what we have to do. Well, I'll use it in another color, in one. How many steps is this? Well, that's one step, right? So that's actually not gonna influence anything. Now, everything happens in the while loop. So it is really important to know how many times will the while loop be run. Now remember, when you analyze something like that, you have to think worst case scenario always. So what would be a worst case scenario be? Look, what we have to do. Let's look at the first of the tasks. Find the talk T with earliest end time. How do I find that? In that sense, I'm cheating a bit because I don't describe what I have to do here. But what I should do is, well, I can use one of my search algorithms to find the T. But that's not how it works, because I have not ordered my list yet. So if I want to do that, I have to first order my list and then do the search. Let's assume that I don't care about that, and you'll see why it's better not to. So I just have my list. People have sent me via email, I want to do this talk at the Zoom meeting at this time. I don't want to, instead of halls, I think this is pre-COVID, right? So let's, instead of a hall scheduling, let's say a morning schedule where we do Zoom meetings, okay? This guy says, I have my Zoom meeting set up there, this is my Zoom meeting, this is my time Zoom meeting, and they email this to me and I get them in different order. So I have a completely unordered list of starting and end times. In the book, in the textbook, they describe a little bit how you can order all that. Forget about that. Let's not do that. Okay, so okay, what happens then? So I have to find that talk, and I have to use one of my search algorithms in an unordered list. The best thing I can do is just go through the whole list. So I will have to go through the whole list. It could very well be that the talk with the earliest end time is all the way in the back. So worst case scenario, n steps. This is the number of steps, right? So the number of steps in red. Then I have to, when I have this, I add it. So that's just one step. That's just adding. And now the removing part. That is a bit tricky, because what I have to do here, well, again, let's think, what should you do? How do you remove something? You look at the remaining talks and then see whether either the end times conflict, there is a conflict. In other words, I have to make a comparison with every single element in L and T. Every single element in L that is left in L and T. So this gets now a little bit trickier. Now you could say, is there a payoff? You say, well, okay, professor, you say you have to do this n times. I agree. The first time you have to do this n times, but then you will have removed some stuff, so you're going to have to do it a few lesser times. Sure, that is true. But worst case scenario, here's the worst case scenario. The list I give you, these are the times I'm giving. I'm going to put them in a roster here. Let's see. This is the roster. Suppose the times that I am given were this. Okay, so what I'm going to do, okay, this is talk 1. No, I'm going to use a different color. I don't want the, sorry. So let me give you an example, very short. So here is 8 p.m. and here is 12 p.m. 8 p.m. and 12. Well, I'm a night person, so as you can see, it's 11 o'clock now. If you wonder in the left-hand corner, why do I use a military term, or am I a military person? No. But who else use military term or use military time or uses 24-hour clock? Europeans. And that's what I'm originally European, so that's why I use that. Okay, so going back to 8 and 12. Okay, here's the first time that was given to me was scheduled here. And the second time it was given me was scheduled here. The third time was this one, and the fourth time was this. So let's say this is the order in which, so this was talk 1, 2, 3, and 4. I don't know why I put it this way. So you see, you see already that every talk will be scheduled. But the problem is that I put the ones that I want, the one that I should take first. No, I'm sorry. Yes, this is what I want, but I just said it's wrong, right? Why do I say the opposite order? This is my first talk that is given. Then somebody sent me this one. I got an email from somebody else. So this was talk A, talk B, talk C, and talk D. So this is the list that I have now. And okay, sorry. It is the other way around. Sorry. It was the way I said. I got a little bit confused here. So, okay, this is the first one they sent. So I should call this A, and this call this B. This is C and D. Let me just use the letters here. So you see that the very first time I'm looking one with the earliest end time, that would be D. In other words, but remember, this is the list that I have. So I first go to A. No, that's not it. B is not it. C, not it. D is the one with the earliest end time. So I pick D, the last one in my list. Now, that I'm adding that. And then I remove all talks, but I'm actually not removing that much. I'm just removing one because nothing conflicts. I'm looking at the worst case scenario from this point of view, from this algorithm, right? If I only have this, then I still have to do 3 more. So in the next step, okay, instead of n, I have to do n minus 1 times, and I will remove 1. And that will be n minus 2, and so on. Now we have seen this already. When you keep removing only 1 at a time, then you could think of this as the total number of steps is the sum of the first n numbers, right? But that is still, if you add that up, it's still n squared, O of n squared. Now let's be a little bit loosey, and say, okay, n, the size of the length. Now what do I do here? I haven't said that yet, but remember, if this is the first time, that is my first t, right? It's the one that starts earliest, ends earliest. Now I have to make sure that I erase everything that is incompatible. Although in this case nothing has to be erased, but I don't know that, so I have to compare it with the first one, with the second one, with the third one, and then with itself. So n comparisons again. This is in the beginning. Now, as I said, when we keep going a little bit less and less, it becomes perhaps the list gets smaller and smaller, but it won't change the complexity. So in total, this is 2n plus 1. Now, how many times do we do this? And this is where I'm getting at. Well, I keep whittling down the list by, in worst case scenario, by 1. So this will be carried out n times. And here in this case, you see, I have to do this algorithm 4 times. Because each time I'm going to pick one of these, and each time I have all the rest is still compatible. So the list only gets smaller each step by 1. Therefore, I have to do n steps. So I have to do the while loop is going to be carried out n times. So let's write down the complexity. So what's the complexity? We have the 1 here. Let's work this 1 here. Then we have n times. That's the while loop. We have to do these guys here. That's 2n plus 1. So that is 2n squared. Oops. 2n squared plus n plus 1. Just rearranging, which all this doesn't matter. This means O of n squared. So this is a polynomial time, quadratic time, as we now would say. And you could try to see, perhaps can I do better? And I say yes, things will actually, the list that you get here will get smaller, but in worst case scenario, only 1 by 1. This, therefore, also, because again, you're looking to the same list, but you have to go through the whole list. Whatever size list that you have here is going to be the same size here, worst case scenario, right? Always worst case scenario. So the first time is 2n plus 1, the next time is twice less, and non-again twice less and twice less. But if you calculate, and that you can say the sum of all these numbers, that's how many times I will carry out the whole thing. But if you look at the formulas that we have for the sum of the first so many numbers, it is O of n squared. So it's the same complexity. Now, comparing what about sorting a list? Sure, you could have sorted this list first in whatever way. The textbook has this, as I said, I think it gets lost a little bit in its sorting there, but you can do it. And that we have now seen, we have sorting algorithms that are, no, we haven't seen even that, yes. There are sorting algorithms, but that is for discrete math 2. You will see there are sorting algorithms of complexity O n log n, which is less than n squared. So what that means is when your actual algorithm is O n squared, you are, if you do inside something of lesser complexity, it's not going to affect, if you do it only once, of course, then it's not going to affect the overall complexity. So I could have done that, but you see, it doesn't gain me anything. Right? Okay, then you say, okay, fine, but then it's easier to, if you have a sorted list, then what we just talked about here in ternary search, you can do it in time O log n. So this doesn't take n steps, but O n steps. True, but this one is still problematic. But here are several things that I have to remove. And perhaps, okay, if you see it, you could perhaps also do this in log n, and then you might have an improvement. Then it would be, this would have to be carried out, perhaps. No, see, this is always going to be the problem. This might be, you might be able to do this quicker, like in log n time, but this you can never do quicker, because we see this here in an example. In the worst case scenario, you're going to have to do this n times. You're going to have to do one at a time remove. No matter how smart you are, if the list is given this way, you have no choice. So I think, in general, this is O n squared. Now, I'm not saying that there are no clever people that can do scheduling much better. Okay, I'm trying to remember whether I've seen one. I don't remember anymore. But you will see in discrete math 2, we will do some of these things better. And that is important, because these are, of course, important problems, right? Scheduling, searching, sorting, these are all important problems. We want to do this as fast as possible. And now, today's lecture, you see that it has the big difference between log n, polynomial time, and then the bad part, exponential time, right? Okay, so that was for the homeworks. I hope it was clear enough. As I said, the only way to get hang of this is by doing many examples and looking at them again, trying to figure out yourself. This is important, right? Okay, I gave you the example now, but you should be able to figure it out yourself and even do the argument without looking, so that you somehow say, okay, I get it now. I get where everything comes from.